Hi, I'm Matthew Hong from Toyota Research Institute, and I'm happy to present our wheel design case study on behalf of my co-authors. So I want to start this talk by giving you a 1,000 feet view of the automotive wheel design process and ground it in a real-world example. It starts with a product planning group generating a key phrase that captures the product that they want to build. In this case, it was a badass adventure machine for the 2024 Toyota Tacoma. Once the body design is settled, product designers start working on wheel styling by proposing a pair of style keywords like rugged and luxury, as you can see on this image, and graphical style renders in order to focus their design space. This two-dimensional mapping space is used as a means to ensure proper alignment between the keywords, proposed styles, and the target market segment in discussion with the sales team. Now, once the wheel designs are settled, they are sent to the engineering group to apply engineering and manufacturing constraints to the rendered styles. In one scenario, the designs will be deemed engineering feasible and sent to the manufacturing plant to begin the production process. In another scenario, for a major redesign like the Tacoma, consumer aesthetic perspectives are captured through design clinic sessions, which require significant investment to collect subjective ratings of different semantic attributes, such as sportiness and luxuriousness, from potential consumers. So, the motivation for our work is styling, which focuses on the process of connecting semantic expressions of human aesthetic perceptions to design. When we look at the problem space of styling, it mainly exists in these two areas. First, sketching wheels and exploring the design space takes too much time, and any opportunity for getting consumer feedback on aesthetics happens too late in the process and is detached from the styling process. The significance of these problems is that they create risk in the overall production process in terms of production cost, where time equals money, and poor alignment with consumer preferences. So, our main goal is to improve this process and alleviate some of these risks through rapid design exploration backed by consumer perceptions of aesthetics. Today, we have generative models like GANs and text to image diffusion, and tools that offer quick and intuitive ways of translating semantic expressions to visual representations, as you can see in these images. But applying these tools to professional product development practice is problematic for two reasons. First, because of the non-deterministic properties of AI, there are limited means to anticipate the outcomes of these models based on text as an input modality. Also, it's unclear whose aesthetic assessments are represented in the design outcomes. So, how can we design an AI assisted design process and a tool that helps designers better connect semantic expressions to visual representations? To answer this question, we interviewed a small team of experienced designers in a US based studio of a major OEM in the automotive industry. Through this, we were able to understand their current process, pain points, and opportunities. Specifically, we identified three stages in their current process that helped us formulate three goals for system design. So, what did we learn? First, in the data collection phase, we learned that compiling reference images from other OEMs was a tedious process, which was also at risk for design fixation. So, we wanted to support an efficient and flexible means for exploring multiple design examples by organizing them in an intelligent way. In the second stage, as we saw in the previous slide, designers create a two-dimensional mapping space of reference images along semantic attributes such as luxury and rugged to build consensus toward concrete design directions. But the mapping process suffered from dealing with so much ambiguity in the design language. For example, even designers in the same team had a different understanding of what luxury meant to them. We saw this as an opportunity to project consumer perceptions of aesthetics directly onto the map. Finally, we learned that designers often explore novel designs in a focused design space by combining two different concept designs, but end up spending significant time trying to realize the shape of each combination. So, our goal was to support fast and low cost generation of new design ideas by merging them at the pixel level. For each of these goals, we found an opportunity to incorporate machine learning and human aesthetic assessments into the design process through computer vision based clustering, gathering consumer ratings of style aesthetics, and diffusion based interpolation. Here's the full machine learning pipeline, and more details of the system architecture and technical implementation are described in our paper. From these three design goals, we developed the Wheel Design Space Organization System, or Wheel DSO, which consists of a style map that's organized by visual features, comparison map that's organized by consumer perceptions, and style mixing panel that enables diffusion-guided image generation through interpolation. So in this video, you can imagine how a designer might use this tool, where they first look through many wheels in the style map to understand where the market is and emerging trends organized by similar visual features. Selecting each wheel places them on the comparison map, which helps them understand what consumers actually perceive as being luxurious and rugged. And you can see here that selecting different style keywords changes the relative position of the wheels. Finally, with the style mixing panel, the designer can then perform a series of visual style mixing experiments using two selected input images until they see something that captivates their mind. We ran a pilot user study with 10 automotive designers and found that being able to see diverse style combinations in a matter of seconds opened up a whole new way of thinking about design. Because instead of using the time to sketch, they can spend the time navigating and discovering new pockets of design spaces and make quick decisions about what works or not. For example, one senior level designer told us that the tool allows them to detach themselves from a few inspirational benchmarks and explore a diverse range of combinations that they might not have thought of. So going back to the example of designing a truck wheel, instead of trying to benchmark other truck wheels and risk becoming fixated on a few examples, designers can potentially make bolder moves by combining a truck wheel with a sedan style. Exploration is great, but designers also need to focus their decisions. Through our study, we learned that designers want to move away from speculation and validate their preconceptions about human aesthetic judgments against consumer data. So they wanted to engage with consumer data more directly, as you can see in this quote from another designer, perhaps by contesting them, before committing to a few design choices. Last but not least, we saw the potential for AI-enabled ideation and visualization to increase communication efficiency among designers and even across different stakeholders. In fact, one designer hinted that using abstract forms of communication in design review meetings tends to add more time needed to resolve any ambiguity in subsequent meetings. So instead of saying, let's see what happens when we merge style A and style B, the conversation can evolve to focus more on concrete changes to be made about a particular design as a result of the interpolation. Okay, to wrap up, we contribute a novel system and framework that facilitates design exploration with consumer data by organizing existing designs, integrating consumer information, and generating new ideas. Through this system, we saw the potential for AI to support rapid exploration of ideas and design time communication through quick visualizations of consumer data and style mixing outcomes. This leads to new opportunities for design practice, such as doing more strategic design thinking with consumer data. Moreover, we found that the zero-shot interpolation technique enabled designers to better anticipate the outcomes of the design combination because the design space was bounded by two reference images of their choice. Based on this study, our future work will focus on supporting designers to better express their intents with multimodal input when using generative models. Thank you for listening.